You should get your little warning now popping up saying you are about to be recorded. If you stay in the session, you are participating in a recorded session on Zoom that could be, and is very likely to be, well, let's be honest, is going to be posted to the course website. Please be informed of that. Please be aware of that. I don't want you guys to be caught off guard. Thank you. And I also don't want to be sued for recording someone without their permission in the state of California. Okay. All right, so to begin with, we're looking at homework question 1.81. And that question is aluminum has what we call a specific heat of 0.215 calories per gram degrees Celsius. I just need to know whether it was calories or joules. Okay, so that's the first piece of information we're given. We are told then when I think it's 25.7 grams. No, sorry, calories. My apologies. Reading too fast. 25.7 calories. And then in parentheses, they tell us that that is 108.5 joules. Is added to 18.4 grams. There's the grams. 18.4 grams of aluminum. Oh, by the way, guys, if you do not know your symbols for the elements, make flashcards, purchase flashcards, get flashcards, start learning them. Okay. You don't need to memorize atomic numbers. You don't need to memorize atomic masses, but you do need to be able to recognize the symbols. If I say aluminum, you better know that's Al. If I say hydrogen, you better know that's H. If I say iron, you better know that that's a capital F and a lowercase e. And I'll provide you a list that you need to know. And the exams will come with a periodic table, but a periodic table with the symbols. Okay, so what is the final temperature? So, okay, so it starts at, it's supposed to be an at 20 degrees C. So that 20 degrees C is the starting, let's call that the initial temperature. The actual question that we finally get to is, what is the final temperature? Now, let's see, blah, blah, blah. 777. Does anyone know where we would start with this question? Well, a good place to start is identifying the information available to you. Okay, so does anyone need more time with this slide? Does anyone need more time with the slide? Okay, I'm going to pretend like you guys got that all copied down, or if you don't, you have the book in front of you. One way or another, you got this source. Now, or you took a picture of the screen, whatever. With that in mind, let's actually write down the useful information. You've got a specific heat capacity. C subscript SP is usually how we say specific heat capacity. And then in parentheses, we usually put Al to indicate that it is of aluminum. And that is, as you can see from the previous slide, of course, 0.215 calories per gram degrees Celsius. We also know that we add 25.7 calories. We know that this is added to 18.4 grams of aluminum. And we know that the temperature that you use a capital I, a capital T, it's a capital T, use a capital T for, and then we usually put a lowercase subscript I on it for initial temperature, starts out at 20 degrees Celsius. Okay. So what are we looking for? We're looking for final temperature. How does that work? Let's see how you put this. Let me give you guys an equation. I don't think it actually does it? No, it doesn't give you the equation here.
The book shows the equation for 1.80, but yeah.
Ah, okay. Well,
Yeah.
there is an equation, and actually, they kind of give it to you, just spelled out, not using symbols. So the equation that they give you, and the one that people tend to use, there's a couple of different options, but the one that they give you is heat in parentheses of calories is equal to the mass in grams times the change. Is everyone familiar with delta for change? Is anyone not familiar with the use of delta for change? Okay. Triangle or delta, the Greek letter delta in this case, means change. And so if you see something like a delta T, what that actually means is temperature final minus temperature initial. Whatever the delta is in front of, delta X, for example, would be X final minus X initial. Okay, does that help? I hope. Does that make any sense? The delta represents a change, and it's actually looking at the difference between the final condition and the initial condition. Okay. And yes, I know your book doesn't teach you that, but I like to go a little bit beyond that and give you guys some more information if you haven't been exposed to it, because you might encounter this in another class. And now you're ahead of the game. You don't have to experience it again for the first time, unless you have a very bad memory. But that is not something that I'm going to assume anyone has. So delta T is what goes next, which is the change in temperature, because T, as we said, T equals temperature. And finally, we multiply that by what the book says next, which is the specific heat capacity, okay? And that is going to be symbolized, like I said, here. So see this? The letter C, subscript SP, is how we represent specific heat capacity. So you can do this two ways. You can put in parentheses specific heat capacity, or you can do what I do because I'm lazy and I learn symbols and I write out equations with as few uses of my pen as need be. It's all about, and I'm not lazy, I'm energy efficient. I have been energy optimized for this era where we need to conserve energy and protect the planet from too many fossil fuels. So I'm actually trying to save you guys by having a lower carbon imprint by less effort on my part. Just pretend you like my jokes, okay? Just pretend. And you don't even have to laugh. You can turn off your camera if you don't want me to see you looking at me going, shut up. You can turn off your camera. Or honestly, I think I usually minimize your cameras anyways. But it is nice to see you guys laughing. So every now and then I turn to a random camera just to boost my ego. Okay. That again is not true. Don't worry, guys. I scared someone off. We now only have 23 people. Darn, lost someone. That's sad. That breaks my heart. Or it would if I had. Okay. So how to do this question? You just start plugging in numbers. or actually what I would do first is manipulate the equation. So the first thing is manipulate the equation to set up what you're solving for. Okay, now the question is, do you know what you're solving for? Of course, because if you don't know what you're solving for, then how can you set up to solve for something, right? Just like if you don't have a destination in mind, what's the point in having a map or GPS or getting in the car and driving somewhere? Well, okay, fine, you can go on an adventure and just start driving, but that's not the point. Stop arguing with me. That was the voice in my head, sorry. No, it's never told me to kill people. Okay, so ask yourself first, what are you solving for? And we said that on the previous page. We said that we are solving for temperature final. We're looking for that final temperature, okay? We know the initial temperature, we know the mass, we know the heat that is added, and we know the specific heat capacity. So there's only one variable that we can solve for, and that's important also because for an equation like this, you can only solve for one variable. If we had more than one unknown, this would be a problem that you could not solve. And in a problem like this, if you happen to come across one that has more than one unknown, very likely you're missing a piece of information that you didn't find properly. Okay. Yes, very rarely questions are written wrong, but 9 times out of 10, you guys missed something rather than the equation or the question being wrong. Okay. So what are we solving for? Final temperature. So let's set up our equation and let's solve for that. You guys okay if I change slides? Okay. So very quickly, heat is equal to, equation was heat is equal to mass times change in temperature times specific heat capacity, okay? Now let's plug in a few more things. So heat is equal to mass times temperature final minus temperature initial times specific heat capacity. Let's identify what we're solving for, final temperature, okay? That's the one we want to have everything set equal to. The thing that we're trying to solve for is the thing that we want to have set up for finding the solution to, okay? So now that we know, sorry, I shouldn't point. People get very upset when I start pointing, even though I'm just pointing at the camera, not at anyone. Anyways, we're trying to solve for this thing. So very quickly, we do some manipulation. You start probably dividing both sides by mass and specific heat capacity. So you end up with temperature final minus temperature initial is equal to heat over mass times specific heat capacity. So, and then finally, let's isolate final temperature and get that as heat over mass times specific heat capacity plus, because we'll add to both sides, it's plus. We're adding to both sides the initial temperature. Okay. Did anyone not follow that? Colby, I'd recommend putting your hand down. That's got to be getting sore by now, man. You know, let the hand rest. I'm just joking with you, but you set me up for a good joke.
You made my girlfriend laugh.
Good, fantastic, awesome. We need more laughter. Okay, so the temperature final. Now we just plug in our numbers. The heat, remember, if you've forgotten, I'm going to flip back real quickly. The heat was 25.7. So 25.7 calories divided by, we're going to use 18.4 grams. And then finally, the specific heat capacity is 0.215. So 0.215 calories per gram times degrees Celsius. Now, it is very important, and I will always tell you guys, and the purist in me always wants to take points off exams when people don't write their units on there. Okay, so the question I missed was, when do we plug in the numbers? I always recommend my own recommendation and my own preference personally is to plug in the numbers once I have it set up for what I'm solving for. And the reason to do that is, if you're using symbols, it saves you so much time. If you're writing out all of these long numbers with their units, you lose so much valuable time, especially on an exam, that you could do so much more with, like artwork that your professor will someday get tattooed on his body. Okay, you have so many other options. Staring at the ceiling, okay, leaving class early after the exam. Now, whether or not we'll be doing an exam and a lab on the same day, I haven't figured that out yet. It's not likely, but I haven't figured that out yet, and I don't make promises when I can't keep. Set your equation up if you can, if you're comfortable with the idea, before you plug the numbers in, because you won't make mistakes like copying down the wrong units multiple times or writing down the wrong number sometime after you've written these numbers 3 or 4 times. You make fewer mistakes if you write fewer things, okay? Now, if that's not what you want to do, it's not a requirement. I'm not going to grade down your exam if you don't go about this the exact same way that I do. This is the way I do it. If you don't do it this way, if you decide to plug in the numbers from the beginning and write everything out and manipulate everything, I empower you to do what you do as long as it's legal to the chemistry that we're doing, valid, and gets you to the right answer. Okay. So at the end of the day, though, you plug that in. And the reason it is so important to label everything with units is that is going to help you ensure that you actually get to the right answer. One of the things that if you've ever worked with units, you already know is that if you set up your units properly, everything will cancel and give you only the remaining units that you need for your final answer, okay? And unit cancellation has saved me when I was an undergrad so many times. It saved me so many times in high school, saved me so many times in grad school, has saved me so many times when I was teaching, has saved me so many times when I was working and prevented me from poisoning someone. Yeah, I've done things like test water for water treatment plants, and that's an important thing. Testing water for wells, making sure people don't have bacterial levels that are too high or heavy metals. If you do these calculations wrong, you might poison someone. It's not a good thing to do. I'm not saying you guys are going to kill someone by doing the exam wrong, but you never know. Maybe you'll break my heart so much by doing so poorly on your exam that I die of an aneurysm. And then you end up with a professor that's not nearly even half as funny as I am. Okay. Or good looking. Okay. I'm vain. I look in the mirror, I go, damn, still got it. Okay. So, and I know I still got it because my wife is still here. She's still married to me. She hasn't left me yet. So I must be doing something. Okay. So I'm not even going to waste time plugging this into the calculator. I'd rather spend the time making jokes, but you get the general idea. Okay. And I'm going to show you guys the unit cancellation. Calories cancel with calories. Okay. Grams cancel with grams. And you're left with, I'm just going to use squiggle as the numbers, divided by degrees Celsius, which when you divide by something is equal to squiggle degrees Celsius. Okay. That's why units are so important. And I will emphasize them on every example I do as a calculation. Write down your units, write down your units, write down your units. Please, please, oh, please write down your units. Okay. Any questions? Oh, I see that there's 4 things that have gone on in the chat. Let's see what we're missing here. Anyone know where the chapter 1 lecture is? Chapter 1 lecture is composed of other people's videos on the module on the lecture canvas. And I will emphasize that multiple times. Okay. Yeah, exactly. They are broken down into modules with different videos. And hey, the great thing about that is you guys don't have to listen to just my voice. You get to listen to all sorts of other people's voices. There's a mixture of people of different ages, different ethnic origins, I think. Pretty sure I've posted multiple genders. Well, at least 2 genders. Whether there are 36 genders now, I've lost track. And that's not a joke, I just have. I don't know how many genders there are out there now. But there are at least 2 genders represented in the modules posted. Okay.
I have a question on
Certainly.
the answer. So for significant figures in this, there's the 20 degrees Celsius, which is 1 significant figure.
Ah, okay. So yeah, that is a problem with this question. Yeah, because on the exact question that we're looking at, it is actually 20 degrees, right? It's
Right.
not actually got a decimal, does it?
Oh, I'm not sure.
Okay, I'm looking right now. I'm trying to flip back.
No, there is a
There it is, it's
decimal. I take
20.0.
it back.
Yes,
Never
no.
mind.
Yeah,
Yeah.
I think that's my bad. I think I wrote it as just without one, but the
Yeah.
temperature initial is actually 20.0 degrees.
Okay, so it's
Okay.
3. Okay.
Yeah, so you are
Okay.
correct. It is 3 sig figs. Exactly. That's
Okay.
excellent. That's excellent use of your knowledge of sig figs that you guys have undoubtedly gained from my course, because you didn't know anything about these topics at any time outside of my course. I have imparted this knowledge to you.
Okay. And then I had last question because I
Sure.
did all the problems, but most of them don't have answers in the back, so I don't know if I did them right or not.
Okay, so two extremely quick responses to that, I promise. I'm surprised that, oh no, you're right. This edition of the book doesn't have all the answers in the back of the book.
No.
And I was surprised by that because they used to do that. So that's irritating. And I wish we had a better source on that. My second response to that is your grade is not based upon reaching the final answer.
But I'd like to know if I did it right.
Fair enough. Absolutely. True enough. Okay. So what I will consider doing is finding the answers or calculating them myself. And after the homework has been turned in by most people, posting answers. I won't post like how to do the homework. I won't post
Right.
like a how to, because that'll just give you guys something to copy down and then turn in and get full credit for it. But I'll give you answers. Because if you turn in just an answer sheet, that doesn't count. You got to show a little bit.
No, that would be helpful though. Thank
Okay,
you.
absolutely. Yeah, no, I'll add that to my impossible list to do.
Okay, thank you.
No problem. And I'll probably forget, so probably send me an email.
Will do.
Okay, yeah, I'm just being honest. There's so many things that I got to do. So for the equations, what for these equations, we round, correct? Would you like us to be significant figures for all problems? It's good practice to do significant figures for all problems, and it's good practice to put your answer always in scientific notation. I will, however, say that if you forget to on an exam, if you forget to, and I haven't explicitly put instructions on the exam, and even more importantly, on the question, or I should say, most importantly, on the exam. So the exam, if I expect you to answer with significant figures and scientific notation, there will be explicit instructions on the exam saying every possible question must be answered with scientific notation and significant figures, if I'm going to do that, okay? I will be very clear about what is expected on an exam from you guys. And if I'm not, and you don't answer it with significant figures or scientific notation, and it's not clear, you guys get the benefit of the doubt and you get the full points, because if I'm not clear on the instructions, that's my fault, okay? That's my fault. Even if I put in the syllabus, which I didn't, but even if I did, if it's not explicit on the exam, you guys will not be held accountable for it, okay? I need to be clear about that now and make sure that you understand that. And if I try to hold you for something that I'm not clear about, just let me know, okay? If you feel like I'm grading you guys unfairly, as long as you're not asking me to give you credit for something that you didn't do, if you feel like I'm grading you unfairly, in the very least, you can express your concern. I may not necessarily agree with you and it may not change anything, but please, you have the opportunity to express your concern, okay? And you won't be marked down for expressing the concern as well. I should mention that. There is no penalty for saying, hey, do I deserve a few more points on this? As long as you didn't take the exam home and then grade it yourself, okay? That's the only caveat. Page 14, dry lab L. Okay, I think we have enough time for that one. That will probably be the last one we do tonight, but I think we have enough time for that. Because I want to leave myself some time to actually be able to lecture, because as you guys can tell, I love to talk. I love to talk.
Well, we're not completed with this one, right?
Oh no, this problem's done. I'm
So
pretty sure.
how about the TI? We didn't put the plus sign with the TI.
Oh, you're right. Thank you.
Yeah, welcome.
Thank you. See, even I, on occasion, can make mistakes. Okay, so I don't consider myself to be perfect every day. Some days I am perfect. Today, I made a mistake. And see, if you see something that doesn't look right, please let me know, like you just did. Thank you for doing that, okay? So it should be plus 20.0 degrees C is equal to squiggle degrees C. That's another way that you know that your answer had better ended degree C, and that everything in this thing should better cancel out to degree C, because you can't add anything together that have units that are different. So thank you. All right, anything else, guys?
I just wanted to clarify, do we just divide those numbers, times it, and then add it? Sorry, I haven't done math in like years.
Yeah, no problem. Okay, the way that I would go about doing this is multiply the two bottom numbers together first and then divide them into the top one, or you guys are allowed calculators, okay? So you can literally enter into your calculator the top divided by, in parentheses, the two numbers multiplied together on the bottom, and then finally add the 20. If you were going to do it by order of operations, you'd actually want to make sure that you had a parenthesis here on your calculator, and you'd want to make sure you had a parenthesis here on your calculator, just to ensure that the order of operations does actually go the way you want it to. It's probably not necessary, but hey, it doesn't hurt to be a little careful. And actually using a few parentheses is not going to cost you a lot of time.
Thank you. Thank you.
No problem. Thank you for asking. Okay. I want you guys to always ask, please. As long as you're asking good questions, I'd be happy to give good answers. And as long as you don't ask me like a question like, what is the temperature outside? We're good. And actually, even if you ask me that, I'll just tell you I don't know, because I don't have a thermometer in front of me, nor do I have the computer available to me that I'm teaching on. This is actually a chalkboard. Okay, so we're talking now about the existing dry lab that is due on Sunday. I think it's due Sunday. So let me pull that up real quickly to just make sure I have the questions right in my head. We're looking at page 14, letter L. JKL. Okay, yes, that's a good question. That is a good question, because what's confusing about this is what are the symbols? Let's see. Okay, so we're looking at the Ka equation, of course. Acid dissociation constant equation. Ka is equal to concentration of H plus concentration of, and that's what the brackets mean, actually. Concentration of H3O plus, my apologies, H3O plus, which is technically equivalent to H plus, but let's get this right and make sure that everything actually looks exactly the way you'd expect it to. H3O plus, then this must be, yes, it is. Make sure I get everything exactly where we want it. So Ka is equal to that times, it should be, go HA, like so. And the question is, solve for H3O plus. Okay. So the question is, please, or what you're looking for is H3O plus. So the first thing that I should just point out very briefly is these are individual variables. That's a variable. This is a variable. This is a variable. And this is a variable. Each one of those complex symbols represent a single value, okay? And I can understand very easily how it's easy to not think that at first. If you're not familiar with this equation, why would you think that? You might think, well, that's A that's now negative, or H times A, or something like that. Okay. Let alone, why would you guys know that actually the brackets are supposed to represent concentration? You have no reason to know that coming into this class. So keep in mind that each one of these things are individual things the way they are circled. So that means you've only got 1, 2, 3, 4 things you're dealing with. Okay. You're trying to get H3O plus by itself. So you start by perhaps dividing by the concentration of A minus and multiplying by the concentration of HA. Like so. All I've done is flip things. I'm actually utilizing the reciprocal rule. I'm multiplying by the reciprocal of the thing that I want to move, is another way of looking at this. But to keep it simple, you could just say, okay, this thing needs to be multiplied out to get it to cancel. This thing needs to be divided out to get it to cancel. That's what I'm doing. Okay. So that means now both sides get multiplied by HA and both sides get divided by concentration of A minus, like so. And so we end up with concentration of HA over concentration of A minus multiplied by Ka is equal to concentration of H3O plus. H3O plus being the hydronium cation. These are all words that you're not expected to know, but I will mention purely because it would make me cringe as a chemist not to mention. Any questions? I hope that helps, clarifies, and makes it a little bit more easy to do. Okay. If there aren't any further questions, let's see, what time is it actually?
Wait,
Okay. Sorry.
is that how we're supposed to end it right there?
Yeah, that's the final end. That's it.
Oh,
You're done.
okay.
Yeah.
My question
this-
is, why?
Why do you end here, or
Oh,
why?
no. I'd like to know the arithmetic.
Okay. Okay. So I am here. I am multiplying by concentration of HA in order to get it to cancel with the one on the bottom. And then here I am dividing, that's G, dividing by concentration of A minus to get it to cancel up above there. And then the algebraic requirement for an equation is what you do to one side.
Right, but that's it.
That's it. Yeah. Mhm.
Okay.
Yeah.
Can it also be like H3O plus is equals to Ka times HA divide whole thing by A minus?
Absolutely. Yes. Yeah.
Oh, that
Certainly.
was right.
Yeah. 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 What you're describing is
Basically, I'm just dividing and then multiplying to the other side. That's what.
Yeah, exactly. Yeah. You are literally flipping the equation using a commutative property.
Yeah.
Which is perfectly fine. Absolutely.
Oh, okay.
Yeah. No, you haven't broken. Here's the key for math in general. As long as you don't break any math rules, you're fine.
Okay.
Secondly, for my class, especially, I love math. And so if you happen to solve math in a different fashion, more power to you. Okay. And one of the things I love about math is that you have different routes you can take to get to the same answer because it's purely logical. There are no, there's no murkiness to math. Math, unlike most things in life, makes sense. It's logical. Okay, you guys good? Any other questions?
I'm sorry. This is the last one. On the lab, again with sig figs, on page 3, would the ones in the problems be considered the sig figs? So there'd be only one significant figure for each answer, because there are a lot of ones.
For which one?
Oh, God. For the atomic mass unit, for the prefix volume calculation, for the mole, for the molarity.
Okay, so with significant figures, for numbers such as 1, those are whole numbers. And so you actually ignore them. You look for the value that has the least number of significant figures. And in general, especially when it comes to exams I write, the exams I can guarantee this on, there will always be a decimal for something that I want you to actually count significant figures with. And that's how it should always be. I have major issues with the rest of the world that decides to have an implied decimal or make your lives more difficult. To hell with people who want to make lives more difficult. If you want there to be significant figures, put a decimal there.
Okay, thank you.
No problem.
I have another question for the self-test for math skills for perception composition, solving for X in the questions.
Which one, sorry?
Or number 6, present composition.
Okay. And your specific question is?
Solving for the X is 45 is 45.00 is equals to 100 times X over 90.00 plus X.
So your question is, how do you go about solving it, or is there a more specific question? It's fine if that's your question, but I'm just asking.
Yeah, solving for the X.
Okay. Are you okay if I just kind of describe how to do it, or would you prefer to see it on the screen?
Yeah, describing is okay.
Okay, describing is okay. All right. Then what I would do is first divide both sides by 100. Since I'm trying to isolate X, I divide both sides by 100 first. So you end up with 0.45 is equal to the rest of it. And then I would multiply both sides by, in parentheses, 90.00 plus X, and get that to cancel in the denominator of the right-hand side. And it would then be moved over to the left-hand side. Then you would distribute the 0.45 into the parentheses 90 plus X. Good so far?
No, I'm lost.
Okay. My apologies. Wasn't trying to show off, I promise. I sometimes like to show off, but that was not trying to show off. And okay, so I think the question is 45.00 is equal to 100 times X over 90. I'm going to ignore significant figures on this because I just don't want to write stuff out. Okay, 90 plus X, like that. Right now, I'm just going to ignore significant figures. So you start by dividing both sides. That's not a, of course. Okay, so you start by dividing both sides by 100. 100, not anything else but 100. Dividing both sides by 100. You end up with 0.45 is equal to, this cancels here, X over 90 plus X. You then multiply both sides by 90 plus X and 90 plus X, which then gives you 0.45 times 90 plus X is equal to X. Then from there, the next step is this thing gets distributed in. That gives you, I think it's something approximately 40 point something. I think it's 40.05. I can't remember off the top of my head. Plus, but it's close to 40. I remember that. 0.45. X is equal to X. Then you come back and go minus 0.45x, because the next step of what we're trying to do is get both x's together. Okay, you subtract it from both sides. And finally, you will end up with, well, not finally, but the next step. So from here, this cancels, and you then end up with 40 something, approximately 40 is equal to 0.55x. Divide both sides by 0.55. And you get x is equal to, let's see, 400 over 55, approximately. Does that work for you guys? Okay. Okay, I'm stopping the answer question session here, okay? And for no other reason than that was longer than I intended. Okay, so let's see here. Does anyone need more time with this slide? Okay, then we're going to move forward and we're going to go back to where I was in my lecture. We're going to pretend like you guys were with me when I was giving this lecture. Okay, so we're looking at section 2.6 in your books for a number of reasons, but the main goal here is to make sure that I actually get some lecture material up for you guys. And so I want that to be able to actually happen. Okay, so we're starting at section 2.6. And this section in the book is called Electronic Structures of Atoms. Come on. There we go. Okay. So, electronic structures of atoms. Now, this is, of course, why I'm wearing the shirt I'm wearing. Let's see here. Yeah. So the shirt I'm wearing here, and you guys won't be able to see it very well, is a cat equation. It's actually the derivation of an equation. At the bottom here, we've got, let's see how well this will show up. Not very well at all. At the bottom, we've got this equation there, okay? And this equation is what we call the Schrodinger equation. You may have perhaps heard the name Schrodinger. There's a whole lot of important names when it comes to quantum physics and quantum chemistry. Schrodinger is one of those central names, even more important than Einstein. The Schrodinger equation describes the location of electrons in an atom. It describes where they can be found. It describes the shapes of the orbitals. This is the derivation of that equation in the shape of a cat because, well, there's a whole philosophical thing that involves a cat being put in a box with a poison pill. I know it sounds like animal torture, but it's actually just a more philosophical idea. No one's actually done this to my knowledge. The question is related to a whole other thing. And if we have time, we'll go into that. But where I'm going with this is Schrodinger is an incredibly central figure when it comes to the electronic structures of atoms. Everyone knows Einstein's name. Not everyone knows Schrodinger, but Schrodinger is incredibly important. Awesome dude. Very smart. So was Einstein. Anyways. So let's see. Your book makes a few points here and there. My study guide makes a few others. So in this chapter, in previous sections, we will have discussed subatomic particles, the sections of the chapter. That's a good place to really kind of briefly review as if you guys had been sitting through this entire lecture with me. So the chapter 2 starts with atomic theory and structures of atoms, in which we talk about the atomic theory that describes how atoms are essentially laid out fundamentally, what the concept of an atom is, and how they interact. Then we have elements in the atomic number. The atomic number is incredibly important. Okay, so subatomic particles. You've got the proton, the electron, and the neutron. And those are described in the previous sections, and they're also described in the previous lecture that I recorded. I'm not going to go into great detail about them. This lecture, in fact, will focus on the electron, but I want to just review these things very briefly and point out what I've already covered in lectures that you guys will actually very soon have access to. The proton is associated with the atomic number. And then there's the mass number associated with an atom as well, that is equal to the number of protons plus the number of neutrons. So atomic number and protons determine what element, that says element, just so you know, element, an atom is or is made of or belongs to, however you want to word it. The atomic number, and by extension, the number of protons in the nucleus of an atom, determines what an element, what the atom actually is. The identity of the atom, which is its element, is determined specifically by the number of protons in the nucleus. It has nothing to do with the number of neutrons in that nucleus, and it has nothing, absolutely nothing, to do with the number of electrons surrounding it. The identity of an element, the identity of that atom, comes purely from the number of protons in the nucleus. I cannot emphasize that enough. It certainly is a possibility that could even be a question on the exam, because it is such a fundamental idea. The number of protons in the nucleus determine what element we are talking about. We've got 3 subatomic particles there, and only one of them actually determines the identity. Okay. Now, that identity, however, does not necessarily, the identity has a lot to do with the characteristics and behavior of the atom, but actual bond formation, actual chemical reactions, if we're not talking about nuclear chemistry, occur between electrons. So we need to know where the electrons are. We need to know what they are doing. We need to have cameras on them. We need to be spying on them. We need to make sure that they aren't trying to get away with anything. Okay? So we need to know where the electrons are. And so therefore we need to talk about quantum chemistry, because quantum chemistry and quantum physics are the study of orbital shape and the behavior of the electrons. Okay. Now we won't actually go into the equations. Sadly, I won't even draw or write any of the Schrodinger equations up here, because I don't want to scare anyone off. You can see how scary this t-shirt is. I mean, cats are terrifying, okay? Especially if you're deathly allergic to them, of course, but selfish little bastards they are. Anyways, we need to be able to talk about this in at least general terms, qualitatively, okay? All right, so with that in mind, looking at chapter 2 and not dealing with these notes, but what I actually have in front of me, let's talk about a few other things. I just told you we're going to talk about electrons, and now I'm going to not do a 180-degree turn, because 180-degree turns I'm going in a completely opposite direction. No, I'm going to associate with something perpendicular to this topic, or it's going to feel perpendicular, and I'm turning 90 degrees. Okay, let's talk about light. So, light, and therefore more generally, electromagnetic radiation. I will mention a couple of things about this very briefly, and then we will take somewhere on the order of a 5 to 7 minute break at least, because of course I need to get some water, You guys may need to water yourselves, perhaps plant some plants. I don't know, something along those lines. So light, and more generally, electromagnetic radiation. Okay. If you've never heard the term electromagnetic radiation, you need to look it up, and you need to at least look at a reputable website that has some good science on it. It is fascinating. I could go on and on about this subject matter because it is absolutely fascinating. But light, which is electromagnetic radiation, which in and of itself, you notice the name is a dual name, both electronic and magnetic, okay? Which also actually tells you guys something if you didn't ever realize this. Electronic fields and magnetic fields interact. If something is electronic, it generates a magnetic field. Magnets are capable of interacting with electronic fields. Colby, you've got a question. What's up?
Can we go back to that last slide for just a second, or just wipe it?
Oh yeah, no, I don't wipe my slides, no. Unless it's wrong, we can absolutely go back to the previous slide. Yeah.
Okay, we could go back to, I just wanted to take a picture, make sure I got everything.
No problem. And these slides will be up for you guys. I haven't done
Okay.
it yet, but any slides I create, even if I'm doing a lecture on my own, I generate PDFs of, and then I post, okay? So if you miss something, these will, right now it's dragging a little bit, but soon these will be much more rapidly available to you guys. I just make a PDF out of PowerPoint and they go straight to the Canvas site, okay? Okay, so dual in name, both electronic and magnetic. And that is interesting because there was a Frenchman. I know you're thinking, what do the French have to do with quantum mechanics and light, aside from the Enlightenment in the 19th century? But there was this gentleman by the name of de Broglie, not de Broglie, because he's French. The letters are not pronounced the way they might appear. It's de Broglie, okay? De Broglie came up with this very interesting equation, and the derivation is actually very simple, but his equation in general says that mass is related to wavelength. Okay, so let me actually pause right here because I want you guys to also take a break. And on top of that, I want you to think about this idea. Mass is related to wavelength. We're going to say that de Broglie actually said everything that has mass has a, I'm going to use lambda here, lambda to represent wavelength, and everything, well, I shouldn't say that has mass. Well, everything that has, yeah, everything that has mass has a wavelength, and everything that has a wavelength, in the very least, has a particle nature. Now, I have to phrase it that way because there are some things that have particle nature that we consider to have zero mass. Cliffhanger. Okay. Cliffhanger right there. Think about this. Let your minds wrap around that. Everything has a wavelength. You have a wavelength. We can determine your wavelength. We can calculate your wavelength. You can calculate the wavelength of your car. You can calculate the wavelength of everything in your life. All right, guys, I'm going to mute and stop my video for a second. So we're now resuming recording. Please be aware that you should get your warning sign popping up saying you have been told that this lecture is now being recorded. Okay, so I see that there's been a couple of questions, or at least a question in the chat, which is, are these highlights for this chapter, or are you preparing for another lab? And the answer to that is, I'm not preparing you guys for another lab. Essentially, these are my own lectures for this chapter. Yes. I'm preparing you hopefully for the homework, and in the very least for reading or rereading the text as is necessary. Yes. Okay. So let's see. Where did we leave off? We left off on a cliffhanger from the previous episode of this course. We were talking about this gentleman, de Broglie, who basically said everything that has mass has a wavelength, and everything that has wavelength has a particle nature. Okay, so while this is being recorded, so we had another question sent in, and while this is being recorded in lab, this will appear on lecture. I know this is a bit confusing, but this is the only time this will happen, where I am having an influx of lecture material into lab. I'm kind of being generous to you guys in not spending this time to assign a whole bunch of far more detailed labs. I'm kind of using this as a rest period for lab and saying, okay, we're just going to do some lecture time now. This happens to be one of the heavier, there's a lot of heavy concepts in chemistry, but the quantum chemistry and quantum physics by association, which is almost inseparable, are very heavy topics. They are some of the topics that people struggle with the most. Which of course is why we won't go into great detail when it comes to the quantum chemistry, because it's an introductory course. But despite that, even then, the material necessary to cover to make this feel like we're actually talking about something substantial still gets heavy. So I wanted to spend a little bit more time on this, especially since this is the beginning of the class. I don't want to throw a ton of stuff that's heavy at you guys all at once. I kind of want to give you a little bit of wading into the heavy material at a slower pace. And since I have the option to do so today, I'm doing so. Won't always have that option, but I do have that option. So when I can, I will do that. So not going to waste any more time on my commentary. So everything that has mass has a wavelength, and everything that has wavelength has a particle nature. Okay, so a whole lot of important research went on to prove this associated with his theory, and it was proven that light, we know from lots of experiments, etc., light, no, that's not how you actually speak, that's very improper grammar. Light has wavelength, frequency, because it has very measurable wave properties. Just like sound has wave properties, light has wave properties. And that's something that you guys tend to be familiar with. Light has wave properties. Okay, we talk about wavelengths of light. Even in general pop culture, the idea of visible light being between 400 nanometers of wavelength and 700 nanometers of wavelength is somewhat there. And we talk about wavelengths as if they weren't wavelength. We talk about ultraviolet light, UVA, UVB. You're talking about either specific frequencies or specific wavelengths of light that are carcinogenic. You talk about X-rays, you talk about microwaves, talk about radio waves. We dial in a radio station, and that is being established utilizing the properties of waves. Whenever you're listening to the radio, you're making use of the technology that has been developed because we understand that electromagnetic radiation utilizes wave or has wave properties. And our understanding of wave properties allows us to send radio signals. All this Wi-Fi you're using, all of the Bluetooth, everything that I'm talking about, Bluetooth, all these tiny things, Wi-Fi, Bluetooth, all of those are types of radio signals, and those are all types of electromagnetic radiation. Microwaves that you use to cook, those are types of electromagnetic radiation. X-rays, when those are taken, those are types of electromagnetic radiation, okay? All of these things are electromagnetic radiation, and so they all have wave properties, and our understanding of that allows us to do that. That's science, understanding. So, along with that, studying light, they also found that light has particle nature. And some of you guys have heard of the name used for a light particle. The name is the photon. Now, whether or not you realized we were talking about light particles, maybe you heard it in passing in Star Trek. Fire the photon torpedoes. Photons are particles of light. So photons, a photon is a particle of light. I won't go into the details of the experiments associated with light particles, but if you ever have a question about that, we can do that and talk about the experiments that were done to prove that light has particle properties, and actually it travels in distinct particle packets of light called photons, and it travels in a wave-like fashion. Now, that's all well and good. Why do we care about that? Well, like I said, everything has everything has properties of waves, everything has a wavelength, everything has a particle nature. And one of the first things that was realized to travel in waves are electrons. So electrons, before that, we knew that electrons are subatomic particles. I mean, at the beginning of this chapter, we literally say there are 3 types of subatomic particles. One of them is the electron. It's a particle. Now I'm going to tell you electrons, and I've said this before, electrons exist in orbitals. And if you've read the chapter, if you've at least looked at some information, you'll have come across this word, orbitals. And move in 3-dimensional wave patterns within those orbitals. Electrons move in a wave-like pattern. Electrons have mass. Okay. Electrons have mass. Does anyone need more time with this?
Yes.
Yes.
All
Sorry.
right. No problem. I'll get creative. Let's see. The mass. Let's see. There's space here. The mass of an electron is roughly 9.11 times 10 to the minus 31 kilograms. Incredibly tiny. Okay, for reference, just as a reminder, if you've ever looked this up, 1 kilogram is equal to 2.2 pounds, roughly. Okay, 1 kilogram is equal to 2.2 pounds, just to give you a general idea, since we tend to think in pounds in the United States, because we're stuck on the United States customary system.
Professor, do you mind repeating the mass, the purple like?
The purple squiggles?
Yeah, sorry.
No problem. I understand that my handwriting may not be the most legible.
I was trying to listen and take notes at the same time.
That's quite all right. It should still be on the screen, but I'll rewrite it And it's not going to be on the screen at the moment because I just erased it, but the mass of an electron is equal to 9.11 times 10 to the minus 31 kilograms. Okay. Now, I can tell you in general, I don't test you guys on what is the mass of an electron, pick from these 5 masses. That actually would be too easy of a question because all you have to do is memorize. I tend to go for application of material. There will be some facts that I do test. That's probably not going to be one of them. So don't invest a lot of energy into memorizing that number. Okay. I'll point, if there is something I really want you to memorize, I will make sure to point it out. Here's an example of that. Something you definitely do need to know. 1 centimeter cubed is equal to, does anyone know?
A 1,000 liters.
Not quite. 1 milliliter. But thank you for actually offering an option. Okay, thank you for that. So 1 centimeter cubed is equal to 1 milliliter. That is actually one of the central bridging conversions that you can use in the metric system. It can be very useful. 1 centimeter cubed is equal to 1 milliliter. That's the way you connect cubic meter units to liters. That's the bridging piece of material. I mean, you can memorize other conversions. They do exist, but that's the easiest one to remember. 1 to 1. When 1 equals 1, that's my favorite. And that is one you should know. I know that's not directly related to what I'm talking about right here, but it's an example of something you do actually need to know. Okay. Now, the reason I'm pointing out the mass of an electron is to point out that an electron has mass. Okay. When we talk about light, we generally think of photons as they are particles with 0 mass, because as far as we can tell, they have no mass. That's as far as we can tell. And for the purposes of this class, photons have no mass. However, they still are particles. They still behave like particles. They still demonstrate particle nature. So by that same fact, just because you have no mass does not mean you are not a particle. And just because you have mass does not mean that you do not have a wavelength. Electrons have mass, and they most assuredly travel in waves, measurable waves. Okay. Any questions? Okay. If there are no questions, then I'm going to try to move on a little bit more from here. Let's see. What have I covered there? Yes, yes. Okay. Now, the reason it's important that electrons, and by extension, of course, everything has a wave associated, a wavelength associated with, and travels in a wave fashion, is because electrons travel in waves, their behavior question in the chat, is X representing a number or a multiplication sign? Let's see. So I generally will write very tiny multiplication signs. I do not write large multiplication signs. And if it helps, let's make it a more clear, like dot. That's definitely a multiplication sign. Thank you for asking. If something's not clear, please ask. So electrons travel in waves because electrons travel in waves. Because electrons travel in waves, their behavior can be described by functions. Specifically, what we're talking about are wave functions. These wave functions are associated and described, or I should say come from, are from the Schrodinger equation. Awesome equation, really cool stuff. Quantum mechanics, if I could go back in time, would probably be the topic I would actually go back and get my degrees in. Honestly, I got my degrees in biochemistry, but if I had another option, I would probably go back and study quantum mechanics. It is so beautiful, so elegant. We're talking fourth dimensional calculus, just beautiful stuff. So the Schrodinger equations are what give rise to these wave functions. This also means that electrons are not free to move entirely randomly. Randomly, because they can be predicted by these wave functions. Their movement is not entirely random. There is some finite determination to their movement. Now, we're not going to go into the philosophical implications of that when it comes to the fact that we're discussing the fact also that humans have a wavelength, because that opens a thing that we don't have time for. But the wave function describes this limited, somewhat limited freedom of movement. And from the Schrodinger wave functions, we get three, what we call quantum numbers. Okay, three quantum values, three quantum numbers arise, become available to us, etc., from these functions. Pause here a second if you need more time. Try not to rush through this, but at the same time, I try not to sit here staring at the slides while you guys copy everything down. It's better for you to get some things down and come back to the slides than I sit here and start sounding like talking like this. I'm not going to slow down. So what that means from that is, well, maybe you're wondering what the word quantum means. You're sitting there going, quantum? You've been throwing this around saying quantum chemistry, quantum physics. Now we're talking about quantum numbers. What does quantum mean? Well, that's such an interesting question you ask. Let me make sure I get the specific definition. And I want to make sure I get it very precise. So quantum, according to the definition in the dictionary for physics and specifically, is a discrete quantity of energy. So let's record this. It is a discrete quantity hence the origin of quantum, quantity of energy. So it's a discrete quantity of energy, proportional in magnitude to the frequency of the radiation it represents. Proportional in magnitude. That's another way of saying size, proportional to the magnitude or size to the frequency it represents. Okay, so maybe you grasp that instantly. English language makes perfect sense to you, and you know every single word in the dictionary. So by the definition and the definition of the words associated with it, boom, it's right there. Maybe it doesn't make any sense at all. Maybe English is a completely foreign language to you, and you're actually listening to me and it just sounds like noise. Probably somewhere in between. What we're trying to say about this is that there are discrete quantities of energy proportional to the size of a specific frequency. Okay, and what's even almost more important than that is to say that the quantum, this is going to be circular logic, so bear with me. The quantum numbers are quantized. Okay, the quantum numbers, those three numbers that arrive from the equation, are quantized. And the reason I say it that way is because the word quantized, honestly, is actually easier, I believe, to grasp. What does it mean to be quantized? Being quantized means the values, we'll say this, you can assume or possess, whatever you want to say. We're talking about a photon or electron. The values you can assume or possess are not continuous. They are discrete, not meaning secretive. When we say discrete, we mean specific or defined, and limited. There is not an infinite number of values that these quantum numbers can take on. They are limited and defined. And you can't exist between those definitions. Can't exist between them. Okay? And that is quite different from what we experience in the world around us typically. We're used to thinking about, well, my hand is moving in a continuous movement. The light that I see must be moving continuously. I turn the dial on the radio. Well, that's not a good example because it doesn't actually move continuously. It actually does take on specific values. You probably will notice that there are some values that you can't reach on a normal radio. Okay. You look though at like a rainbow and it looks like the light blends perfectly together. You can't see discrete specific colors exactly. There's a perfect smooth transition. Whereas here we're talking about something that is not like that. Here we're talking about values that, if you are familiar with the term a step function. So if you're familiar at all with the idea of a step function, which is a function where you'll have a specific value, say on the y-axis, okay? You have a specific value that you can take on, and then when the next value that you can take on occurs, it actually moves up to a very specific defined area again. And you cannot exist between those two steps. Just like when you're going up a set of stairs You can't decide to exist between the second and third stair. You can't go, okay, guys, I'm just going to sit on stair 2.5 or stair 2.4 or stair 2.193, etc. No, you have to sit on the second step or the first step or the third step. These are quantized existences. These are stepwise values. These are discrete existences. Okay. Stairs, steps are here, 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 and you cannot be in between. And that is true about these numbers, which means that's true about electrons. Electrons cannot exist in a continuum. They exist at very specific defined places, and they cannot exist in between. So if they move, they jump up and they jump back. They don't just move like an elevator. They move step, 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 step. Okay. And they jump to those steps either. You don't see them existing in transition between those steps. They jump, they jump, they jump, they jump. Okay. Going back to one slide briefly because that was requested, I will do so. I just want to kind of lock into your minds what quantum numbers mean and what quantization means. We're talking about defined values here, and between those defined values, there exists nothing. The being and the vacuum, if you will. Now, any questions about quantum and quantized? Because this is not necessarily the most straightforward idea to think about.
Okay, so quantum. So you're saying that it is discrete like a stair, right? So it's like it can't be like half a number, it can only be like a whole number, right?
Yes, exactly. Well,
And
let me be even
am I-
more specific to that. Sorry, I don't mean to step on you. That's the problem with this, right? Yes, if we're talking about steps that exist as whole numbers, exactly. It may not always be a whole number, but it will be a defined value. Like if we are talking about a step that is labeled arbitrarily 1/2, then you can exist at that 1/2. And if the two steps that exist are 1/2 and -1/2, and there is a quantum number that does that, not one of the three we're about to talk about, there is a fourth quantum number that doesn't come from these equations. And that fourth quantum number only has values of either +1/2 or -1/2 and no other values. It's that quantized, it's that specific. And we will talk about that. Okay. But that is even more specific to the idea of quantization in some ways because it is so limited, there are only two possibilities. I think, honestly, actually mentioning that might even help because if you think about it, if there's only two possibilities, that really gives you the idea of what quantization means. You are limited. You cannot exist between those two values. You must either exist at one of those values or the other value, and that is it. You can't exist in your house or walking to your car, for example. You would either have to exist exactly precisely in your house or precisely in your car, and that would be it. Those would be your only options. You wouldn't get to walk anywhere. You wouldn't get to ride a bike or go swimming. Your two possibilities would be sitting on your couch in your house or sitting in your car in the parking lot. That's it. Hell to be an electron. Okay. Don't worry, I've got a lot more terrible jokes. Please.
And an add-on to the question, what does these quantum numbers have to relate to, like the magnitude in the definition in the frequency?
So these quantum numbers precisely tell us the values associated with the identity of the electron existing in the specific orbital. So these 4 quantum numbers tell us the precise address of the electron and then its specific identity. And once I tell you exactly what these 4 quantum numbers are and what values they can take on, I will explain exactly what I mean. But the idea is essentially, oh, actually, that's a good place to go. You know what? We're going to go to the analogy before we talk about the specifics. Let's do it that way. We're going to talk about the analogy before we talk about the specifics. Okay. So let's say that we're talking about an imaginary person. Okay. We'll say we're talking about an imaginary person. And for this purpose, people can only live 2 people per house. Okay, so every house that we're going to talk about in this analogy, only 2 people can exist in that house. Make sense so far? Every house we talk about, only 2 people can live in that house. Okay. Every house exists. Still doesn't look right. Exists. I'm probably spelling exists wrong. Oh well, that'll become a meme, I've no doubt. And now my only fame in life will be for misspelling the word exist. What a sad existence. Oh well. So every house exists on a specific street. And every street exists in a specific city. Make sense so far? These should be things that make sense to you guys, just in existence in the world around us. Every house exists on a specific street, and that street exists in a specific city, which is how you're able to send mail to a location. You've got an address, and because that every address is unique, you can go on Amazon and order delivery to a unique location, a unique address, and get it delivered, hypothetically, every time. Okay, we'll just go with the assumption of no human error. But every address is unique. Okay, every city is unique, and within every city there's a unique street, and on every street there's a unique house. Okay. Now, the only other thing to this is we go, well, there's 2 people in that house. Who do we know? How do we know who ordered the package? Right? If there's 2 people in every house, we've got to figure out who placed that Amazon order or Walmart order or whatever company you're ordering it. I don't work for Amazon, so I don't want to keep advertising them. eBay, mention a few more names here, Sony, Starbucks, you got the idea. Okay, I don't drink Starbucks coffee, but it doesn't matter. Anyways, so we need to figure out who the person is. So in every house, there are 2 names available to a person, and once one person has a name, the other person must have the other name. Okay, there's always a unique identity to every person, and that unique identity of that person exists in a house with a unique address. That's how we're able to identify every single person, and there's not clones out there that live in identical cities on the same street and houses that look the same with the same name. We don't exist in some sort of dystopian nightmare. We exist where we are each unique individuals with our own unique addresses. Okay, makes sense so far? But for this analogy, in every house, there's 2 names available. Each person has a unique name. That house has a unique address. Okay, good so far? And we'll say that the universe of these houses is a state, okay? So all of this stuff is contained within a state. Okay, so within a state, there are unique cities. There's no two cities in a state that have the same name. And that would be a really messed up world if there were. Every state has no two cities with a unique name. Okay, you may have multiple states that have cities of the same name. For example, in the US, there are 5 states that have a city named Paris. There are other states that have cities named Sacramento. But within California, there is only one city named Sacramento. There's only one Los Angeles. There's only one San Francisco, and the list goes on. You get the idea, okay? Within the same state, every unique city, within every city, a unique street, on every street, a unique house, and within each house, a unique person, okay? Any questions about this analogy? You guys following me so far? Okay, good. Now, let's define these things. So, a state is an atom. Okay, each of those unique states is an atom. Okay, now, each city is what we call an energy. We'll call these specifically a primary energy level, or another name for that is what we call a primary shell, symbolized by the very generic letter N. Now I'm going to go through and name all of the things in this analogy before we talk about these things in detail. Okay, I'm going to break down the analogy into the different quantum numbers that they're associated with, and then we're going to talk about the specific quantum numbers. Okay, that makes sense so far, guys? I'm going to lay this out in general terms, and then we'll go into the specifics. That way, you guys have time to absorb this information. Okay, like I said, this is complicated, and I'm actually exceptionally proud of myself for coming up with this analogy. I'm sure other people have come up with this analogy as well, but I didn't read this anywhere. This is mine. Okay, so now each street is what we call a subshell. Okay, the subshell, and there's only one name for these, thankfully. Subshells are represented by lowercase cursive L, like so. Okay, lowercase cursive L, like that, not with parentheses. So it's a lowercase cursive L. That is the letter, I feel like I'm on Sesame Street right now. This slide is brought to you by the letters N and L. For lack of this spelling, we'll just go like this, like the name, L. Phonetic spelling. Okay, that is the letter L. Any more time needed? Okay, I think you guys are keeping up with me. Now, going on to the next slide. So that was each street, each house is representative is the quantum number known as M with the subscript lowercase cursive l. Okay. This quantum number tells you what orbital we're talking about. That's a bit of a spoiler. I kind of went into more detail than I might have intended, but this will make a little bit of sense. Tying back to where I said electrons exist in orbitals. Electrons exist in orbitals. So that's to say, for this analogy, the houses that electrons call home are orbitals. So electron houses are orbitals, okay? And finally, the name of each electron, because if you haven't quite seen the progress of this, electrons are people. They have feelings too. So don't say anything derogatory about electrons because they have feelings too. Okay. Don't insult your electrons. They might decide to go elsewhere. And then how would you feel if your electrons went elsewhere? You wouldn't exist. And that would kind of be unfortunate. I guess if you didn't exist, you wouldn't know it, but whatever. So the name of each electron, electrons are people, is what we call electron spin quantum number. That is represented by the symbol M subscript S, which actually makes the most sense. It's one of the very, very few symbols that make sense. M subscript S, S for spin. And yes, that is the quantum number that I was talking about of plus a half, minus a half. There are only two values of electron spin. And I will repeat that as we break these again. We'll go back now and talk about the details about these quantum numbers, okay? Is this making any sense at all yet? The reason I wanted to give you the analogy first is electron spin is essentially the name of the electron. And then the other three quantum numbers are its address within an atom. And therefore, every electron within a specific atom has a unique set of 4 quantum numbers. Within the same atom, no two electrons can have the same set of 4 quantum numbers. Okay. I'm going to write this down. I'm going to change slides here. So the atom name is equal to M sub S, the spin, and the address of the atom is described by N, L, and M sub L. And I'll show you just how proud I am of this analogy. Watch this. These 3 quantum numbers right here, these quantum numbers come from the Schrodinger equation. Those are the three quantum numbers that come from the wave function that tells you where the electron is located. Its address is where it is located. Aha. The m sub s, which has nothing to do with where it's located, is the electron's name. Think about that for a second. Just a second. Brilliant analogy, see? Because the name doesn't have to require you to be located somewhere specifically, but the address will always describe where you are located. The function describes where you are located. Sorry?
Can you say that again? Break that down again.
Yes, no problem. No problem. Okay, so let me even write it down. Okay, so remember that the wave function, the Schrodinger equation, wave function, describes location, right? The wave function describes location. These three quantum numbers, the quantum numbers known as n, l, and m sub l, come from the equation. Therefore, those three quantum numbers, these numbers give the address of the electron. That makes total sense. Location is equal to address, right? Your address is your location. Your location is your address. The wave function describes the location. The three quantum numbers, therefore, that come from that equation are essentially the address of that electron. Makes sense, right? I hope. So what I'm saying is the wave function that describes the location of the electron gives rise to these three values. Those three values then are the location of that electron within the atom.
Will those locations be represented in the subscripts always, or does it vary about where they will be compared to where the electron is? Does that make any sense?
I see what you're saying. Yes. Okay. So let me kind of answer that question in a couple of ways. Okay. So the orbital is like a house. The orbital doesn't mean that you are sitting in a very specific chair within the house. You can move wherever you want within that house, right? And you have freedom of movement within that house. So just because you know the address of a person doesn't mean within that address you know where they are. I'm not giving you exact, like, pitch perfect GPS coordinates that lock you in flawlessly to where you are. I'm giving you a general location that's an address that you will be able to find that person within. If you go to that address, you'll be able to go, okay, the person's within this address, and if I yell their name and get lucky, they'll come running to me. Now, granted, an electron's not going to come running to you, but that's the same basic idea. The house is a general location, just as the orbital is a general location of where the electron lives. That's why this analogy is so darn good, because it even works for that bit of detail. Yeah, occasionally I still get chills at how brilliant I was to come up with this. Now, ignore my jokes, okay, please, if you want to. Enjoy them, whatever. The idea here, though, is these three numbers described by the wave function, and the wave function describes the general movement and probable location of the electron, describes an address of where the electron is. It dials it into the specific house that it's living in. And the final thing that we had to do was we realized that electrons exist, 2 electrons per orbital. So do electrons have unique names? Well, it actually turns out that they do. Electrons within a house actually do have unique names. Electrons within a house, or I should say within an orbital, there will always be one electron that is what we call spin up, and partnered to that electron will always be an electron that is spin down. You'll never find in the same orbital two electrons that have the same spin. It is not possible. And as an aside, that blew my mind the first time I heard it. Just a tiny tangent, something that's not going to be on the exam. Okay, this is just a tiny tangent. Photons also have spin. Particles have spin, not just electrons. Particles have spin. So therefore, photons have spin. We did an experiment. Well, I shouldn't say we, but humans did an experiment. So 2 photons were shot, I think through, if I remember correctly, I think it was through fiber optic cable that we used, were shot across a huge distance in opposite directions. From one another. And when they arrived at their destination, they were detected with opposite spins. Didn't matter how far you separated these photons that had been directly adjacent to each other and had opposing spins, fire them off to opposite sides of the globe, they still were detected with opposite spins. They still somehow knew or were aware of their original spin and were somehow linked and could not suddenly assume different spins. And that is fascinating too. That's just something to think about, an aside, okay? So the final touch to that will be something very nice and comforting, which is no matter how far you are away from your loved ones, no matter how much time passes and you are separated from those you love during this pandemic, there are always things that are invisible that link us. Even photons know that. Okay, so just take that in and enjoy that. It's kind of a nice, warm, happy feeling. Okay. A visible example of the analogy I've given. I've never actually created one. I will consider creating one. I'm not the greatest artist with my pen, as you may have noticed, but I'll see if I can like draw some squares and things like that in MS Paint. Actually, I'll probably use the graphic.
You think there's a maybe a YouTube video you could find that could expand on some supplemental
I'm pretty sure there is one, and if not using this analogy that I used, which because I'm certain that I'm not the only one that's arrived at this analogy because it's a really good one. I'm sure that other people arrived there independently. God, my brain is annoying sometimes. The things that this thing spits at me are like, well, tell them about the whole thing in biology about convergent evolution. No, not going to. But yeah, I'm sure I can find one. Yeah, I'm not even going to go off on other tangents that I was tempted by. Temptation, distraction is the way to sin, of course. And I'm joking. I don't believe in sin. I don't have enough time for it. So when they arrived at blah, blah, blah. Okay, moving on from that. That's not going to be on the exam. That's not going to be something. So we go back to these quantum numbers. Let's actually talk about the details of these things. Okay. And I really hope you guys are enjoying this lecture. This is one of my favorite topics in science in general, and in chemistry. This is one of my favorite topics. It doesn't have to be yours, but hopefully you can see the philosophical implications of these things. They have huge philosophical implications. So quantum numbers, the first quantum number, the principal, no, we're not going to say that. We're going to say primary shell, which gets called the principal quantum number of times, but Apparently my brain has forgotten how to spell the word principal, so we're just going to go the primary shell quantum number. I think I forgot to sleep last night. That might be the problem. Let's see. I was too distracted by some thoughts. So the primary shell quantum number, remember, is the letter N. Okay. The primary shell quantum number is the letter N. And for this thing, the primary energy level, this is also associated with the primary energy level is another thing associated with this thing. Okay. It is a region of space around a nucleus that electrons kind of will coexist in within their orbitals. Okay. The problem with describing these quantum numbers outside of an analogy is that they are almost impossible to picture in your head. Because if you think about an orbital and then you go, wait, it's inside a subshell that's inside a primary shell, how the heck does that work? Because you're almost going into something that sounds like it's a fifth dimension. So anyways, the values of N, that's a U, the values of N start at the number 1. So the very first value of N that can exist within an atom, the very first value of N in an atom is 1, followed by 2, followed by 3, followed by 4, followed by 5, followed by 6, and technically goes on and on and on, but there is nothing between 4 and 5. There's nothing between any of these two values given. It is these discrete values that exist. So the first value of N that exists in any atom is the value of 1, then 2, then 3, and so on and so forth. Okay. Couple of other things that you'll read in your book as well. Electrons that are in the same N have approximately the same energy, not precisely necessarily, because remember there's a subshell, but approximately the same energy. Other things, they will spend most of their time in roughly the same distance from the nucleus, and electrons occupying the first N value are closer to the nucleus and have less energy. Okay, so we've established the values of N. We've said that electrons that are in the same N, the same energy level or the same value of N, have approximately the same energy. So they're about in the same energy level. They spend most of their time in roughly approximately the same distance from the nucleus. And those that are in a lower value of N are closer to the nucleus and have less energy. Okay.
Closer to the nucleus, the less the energy.
Yes. Exactly.
So it's kind of like you could, if you're visualizing, it's kind of like momentum. Is that you could?
In fact, it's much more true than you chose exactly the right word. L, our next quantum number, L, is actually called the angular momentum quantum number. So there's even some very well chosen words on your part. Okay, good so far, guys? Okay. I won't always be able to break this stuff down as well as I'm doing right now because time won't permit it. But I'm very glad I get to do this because, like I said, this is very dense material. Okay. And we're not even looking at the equations. We're just looking at this, the properties, the rough properties. I'm not trying to scare you off, just tell you the truth. Okay, so now let's talk about the next one. L is equal to the subshell. Okay, so L is equal to the subshell. And let's see, how do I want to do this? It represents the region of space. I hate writing out all the words because it becomes a long, tedious process. Within an electron primary shell, for electrons with the same energy. So we said the primary energy level, they're approximately the same energy. There are several, there can be, not always. It depends upon what primary shell we're talking about. But depending upon the primary shell we're talking about, there can be more than one subshell within a primary shell. Okay. The subshells represent a collection of one or more orbitals. So within a subshell, there's a minimum of one orbital, but there can be more than one orbital. And there are very specific rules to this. The quantization breaks down further to where there are incredibly specific rules to this. So we'll say the last qualitative thing, which is electron subshell numeric values correspond to specific subshell symbols. Because this does become more complicated, the values gain their own symbols, which I know is going to make it more complicated, but we tried. We tried. Now, the values of L start at 0, then 1, then 2, then 3, continuing up to the value known as n minus 1. Now, take a moment Make sure you get your notes down. Pausing for a second. Process. Okay, n is involved in something associated with the values of L. N, so the specific value of n places a limitation upon what values of L can exist within n. Okay, I'll write that out now.
How does that correspond with your house analogy?
Essentially, the closer you are to the center of the city, the fewer streets exist. Okay, so let's say the way this corresponds is the closer you are to the center of the state, the smaller the city. So the closer you are to the center of the state, the smaller the city, the fewer the number of streets. So the value of n limits the number values of L available. And this is going to get annoying, but the analogy, like you just pointed out, and I appreciate you saying that, David, the analogy actually helps with this. Okay, and we'll see that in a second. So the value of n limits the number values of L available for L within a specific n. Another way of saying that is, so we're going to say this another way, and then we're going to apply the analogy. Okay. Another way of saying that is the subshells within a specific primary shell are limited by what primary shell you are talking about. So the subshells within a specific primary shell are limited by what primary shell you are talking about. The value of n limits the number values of L available for L within a specific n. These are actually the most concise ways of being able to describe this aside from the analogy and showing you how this actually works numerically. So next step, we go to the analogy. Okay, guys, ready? Here we go, comes the analogy. So remember, just to make sure everything is clear, atom equals state, primary shell equals city. Then we have the subshell is the street. And we're just talking about those things. We haven't even gotten to the houses. We haven't even talked about the houses on the streets. We're just talking about the streets. God, no wonder map makers go crazy. So, for the city closest to the center of the state, it is a one-horse town. It is literally a one-horse town. It is the smallest city with only one street. Okay. You go to the next city up from that one. Away from center, you have 2 streets. Okay, so numerically, if n is equal to 1, and remember our rule says L is equal to 0, values going up from there to n minus 1, then for L, if n is equal to 1, the only value available to L is 0. That's your one street in that one horse town closest to the center of the state is the value of 0, the street known as 0. Okay,
So if it was 5, then it could be 4, 3, 2, 1.
Exact 4, 3, 2, 1, 0.
0.
Don't forget
But
0.
It can't be negative.
No negative values here. There will be quantum numbers that can be negative, but here, none available. Okay, this is what I mean by quantization: specific discrete values that are defined, and you cannot assume any other values outside of those defined values.
Are there any maximums for L?
For n, for L, there are no theoretical maximums other than the ones that I've defined, but realistically, there are measurable ones where you go, well, there just isn't a usable value. Essentially, if you put an electron in a high enough primary shell, it'll be so far from the nucleus that the attraction between the electron and the protons will be non-existent, and it will just drift off into space. So from a pragmatic perspective, there are limitations. In the theory, no. Yeah. Excellent questions. Thanks, guys. I hope this is making sense. And yeah, I hope you can tell this is really cool stuff. And I also love the fact that it just makes, as I explained, I hope it makes sense. Okay. Anyway, back to this. So just a couple more examples. Like you said, if n is equal to 5, or let's use in this case even 7. Okay. Don't want that. If n is equal to 7, possible streets within our city known as 7, possible streets, or in this case, to be completely accurate, subshells available are the streets or subshells 0, 1, 2, 3, 4, up to n minus 1, which means we cannot go past 6, 5, and 6. So your electron could live on now 7 different possible streets for the city known as 7. So if you have an n value, it's actually telling you also the number of streets in that city, or the number of subshells available. So that's a little hint there too. Keep in mind, if you know the value of n, you know the number of subshells within n. It also tells you the number of subshells. Okay. Good so far? Okay. And like I said, this is not easy material necessarily. Okay. This stuff made sense to me instantly, but I can't draw a straight line. Okay. I can't paint the Mona Lisa. So we've all got our strengths and weaknesses and abilities. Okay. I am an excellent actor. Right now, I'm pretending to enjoy chemistry. Okay. No, I
So-
love chemistry. Please.
So basically, if I interpreting this correctly, the number of subshells cannot exceed the value of n. So, correct?
Correct.
Okay.
Now, it also means it cannot be less than the value of n, okay? The number of subshells. The value of the subshell can be less than the value of n, but the actual, like if you were counting how many subshells were available within that primary shell, the number available will always be equal to the value of n.
Okay,
Does that make sense?
yes.
Okay. Now, let's make this even more complicated, okay? If this weren't frustrating you enough and you're going, this is easy, I've got it. Let me see if I can make it worse, okay? So, the quantum number known as m sub l. Quantum number known as m sub l. This is the orbital, or at least is associated with the orbital, okay? I should say, and now to even frustrate you, I realize I forgot one thing. So hold on, I'm going to come back to this, okay? There is one little tiny thing that I cannot neglect to mention, and I forgot. You remember how I said the symbols associated with values of L? I said that there were symbols associated with the values of L. Now, this is how you know that things get limited. So, when L equals 0, the symbol is S. When L is equal to 1, your symbol is P. When L is equal to 2, your symbol is D. When L is equal to 3, your symbol is F. And those are the only symbols you need to know. We're not going to go beyond that. Hypothetically, we could go to G, H, I, J, and continue to recite the alphabet for you. But we're not going to do that. For the chemistry that you need to understand, you only need to be familiar with the symbols S, P, D, F. And therefore, that means your best understanding is only going to be associated with 4 values of L. Your actual focus is only going to be on 4 values of L. One other thing, the value of L ends up telling us what the shape, that says shape, of an orbital is. You know how you go to those neighborhoods that all have identical houses? So like a street that has all been built with the same architecture? Essentially, to some, and you go to another street, there's going to be at least a pattern. There may be 4 different types of houses, but in a neighborhood, somehow, for some reason, they decided they're only going to use blueprints for 4 houses. And so you'll see these repeated over and over and over again. These are the sorts of neighborhoods that electrons exist in. Some electrons will exist on a street where there's only the same house repeated over and over and over again. And of course, I've always imagined those as the most miserable of electrons. because there's just nothing different. It's like, hey, electron, yeah, electron, how's your house? The same as yours. That being said, some electrons get a little bit more fancy. Now, so the value of L will be telling us something about the shape of the orbital. Okay, it doesn't tell us exactly the shape, but it'll tell us to some degree the shapes available. Okay.
You missed the L in the writing.
Oh, thank you. The value of L. There we go. Thank you. And that actually worked out better than I had hoped, because if I had used all the same color, it would have been even more horrible. So that worked out perfectly. Every now and then I get lucky. So the value of L, I wish I got more luck like that. It's never the winning lottery ticket. It's always, oh, the color of the letter I chose. No, my luck is very limited. The value of L is telling us what the shape of an orbital could be. It's not going to specify necessarily this orbital is going to be this shape and it's only going to be that shape, but it'll tell you what shapes are available. Okay. Now, let's go back to M sub L. Okay, so I don't want to do this in red. That's saved for other things, like making things stand out. M sub L, in general, this is your orbital. This is the actual region of space occupied by the electron, okay? This is the house. This is where the electron actually lives. God, I'm really pushing it on time here. I know that I've already gone over time. I apologize, guys. Obviously, you don't have to stick around, okay? Just so you know, you're not gonna have to stick around. If I talk to myself for the next 10 minutes, that's okay. No one's grade suffers, okay? So it's the region of space occupied. A house, like we said, can accommodate a max number of 2 electrons. The orbital can only hold up to 2 electrons. So an orbital only has 0, 1, or 2 electrons. Those are the only options available. It's either an empty orbital, an orbital with 1 electron, or an orbital with 2 electrons, and that's it. We know now that it's represented by the letter M sub L. The values are starting at, let's make this a different color to make it stand out. Negative L through 0 up to positive L. Okay, so the values of L can be negative L to 0 to positive L. So if n is equal to 4, possible values of L could be 0, 1, 2, or 3. Now, we have to specify the address of the electron. So this is how I know I should stop my lecture, is when I start making these many mistakes. If n, I almost wrote m. Okay, I was doing so much better. If n is equal to 4 and L is equal to 3, M sub L could be -3, -2, -1, 0, 1, 2, or 3. So in the fourth city, on the third street, there are 7 houses, and those 7 houses are -3, -2, -1, 0, 1, 2, or 3.
So the
Electron-
house defines the parameters.
Almost the opposite direction. The city defines the number of streets available. The street defines the number of houses available.
So they're all dependent upon one another. Is that-
Exactly.
So you
Exactly.
got to, once you get one, then you have to solve your way inward.
Yes. Yeah. And someone has to tell you specifically the value of n is 2. The value of L is 1. Therefore, M sub L is either -1, 0, or 1. Okay. There are so many other things that I really want to talk about here. There's only one last thing I will talk about in this, and this has not even gotten out of this one subsection of chapter 2. Okay. I'm going to try to do these lectures a lot more quickly, but this stuff is very dense. And yeah, okay, anyways, moving on. So we're talking about people living in cities. So let's talk about populations. Right? What is the population of a city? And people care about the population of a city. So I'm going to take that now and talk about how many electrons can exist where, basically. Okay. So every orbital can hold 2 electrons. Keep that in mind. If we look at value of n, value of L that can exist within that n, value of M sub L, then we can look at number of electrons in N, the city, and we can look at number of electrons in L on that street. So if n is 1, the only possible values of L are 0. M sub L, therefore, can only be 0. And the number of electrons in n is limited to 2, because we've only got 1 orbital. And the number of electrons inside of L can only be inside of, I should specify this to, no, you know what, let's start with, my apologies, I'm making this too complicated. Let's talk about one thing at a time, okay? N, values of L, 0, M sub L, number of electrons, 2, okay? If the value of N is 2, possible values of L are 0 and 1, possible values of M sub L are -1, 0, and 1. So for the number of electrons in N, what is that? What do you think it is, guys? Okay. Keep that in mind. And how many electrons can exist within an orbital? If there's 1, 1, 1, it's 2 electrons to an orbital. There's -1, 0, and 1 available as orbitals. So that's 3 orbitals available. So the number of the number of electrons that can exist within n is 6. Or so, no. This is where I start making mistakes because I am getting tired. Okay, within n, it's 6 values here, but then there is, yeah. This is why I should have stopped before this slide, okay? This is why I should have stopped before this slide because I'm actually going about this wrong and I really apologize. You know what we're gonna do? We're going to say that this never happened. So ignore this slide. We'll come back to this material in the next lecture I do, okay? Because I know I'm gonna continue making mistakes. So thank you for your attention. Thank you for paying attention. I hope this stuff's starting to make sense, guys. And I really hope you've had a good evening, all that. Have a great night. Get some rest like I need to. And I'll catch you guys on the flip side.
Night.
Good
Have a
night.
great night.
Thank you.
You bet.